Okay, so in section 6.2, we were working with addition and subtraction, and we did a little bit in estimation, but mostly addition and subtraction of rational numbers. This section we're going to work with multiplication and division. Now, with multiplication and division, one of the nice features of it is that we don't have to have denominators the same to work with stuff. Okay, you can multiply, you can divide without common denominators. So the first thing that this is talking about is with multiplication of rational numbers. If you have a over b times c over d, you can simply multiply across the top and multiply across the bottom. Okay. Now I want to show you what a rectangular region is that illustrates this concept. So if we use this feature, let's just answer the question first, what 3/5 times 3/4 is. I would multiply across the top, right? So 3 times 3. Across the bottom, 5 times 4. And my answer would end up being 9/25. Now I want to show you how you can visualize that happening. Oh, I'm sorry. You guys are awesome at telling me I did it wrong. Way to go. Thank you. All right. So we're going to draw a big old rectangle. I mean, a big fat one. The first thing I'm going to do is I'm going to take my rectangle and I'm going to do the representation for 3 over 5. So I'm going to make my representation as 5 columns. You could do it either way with columns or rows. I'm just going to do mine with columns. Okay, so they should look approximately equal. They aren't too far off on this particular diagram. So this is 5 columns, and I need to shade in 3 of the 5. Now, we worked on this sort of a representation idea last time, right? With these diagrams. So there is 3/5 of my diagram. So far, so good? All right, what I'm going to do next is I'm going to create, from the same rectangle, a diagram that represents 3/4. What I don't really want to do is I don't really want to create the diagram so that it has columns, because I already did that. If I create more columns, it's going to become very confusing. It's not going to be especially helpful either. So instead of doing columns for the 3/4, I'm going to do rows. So we're going to divide this into 4 rows. Again, they should look approximately equal. If they don't, just use your imaginations to pretend like they are. All right, what I'm going to shade now is I want to shade 3/4 of the original blue diagram, because that's the 3/5 diagram that I really had. Okay, I'm going to shade in 3 of the original, or 3 of the blue rows. So that looks like this row. And this row. And this row. So the imagery would look something like this. I'll create a word problem that explains what's happening here. You've got a garden plot. All right? In the garden plot, 3/5 of the garden is going to be vegetables. Okay, that's the blue. So everything in blue is going to be vegetables. Of those vegetables, 3/4 of the vegetables are green beans. So I'm shading 3/4 of the blue rows because it's 3/4 of the vegetable rows. Not putting the green beans where the flowers are or whatever. Okay? Here's the cool thing. The answer to your problem is what's shaded. How much of this whole diagram is shaded? The final shading that we did, the green beans. 9 boxes. 9 out of how much of the whole garden plot? 20, because there's 20 small little box plots, if you will, or boxes in my diagram. Does that make sense? Okay, so this is a rectangular description of what happens when you multiply fractions together. Some properties. As we're doing multiplication, we have a multiplicative identity and a multiplicative inverse. The multiplicative identity is not unique to fractions. Okay, the multiplicative identity is the number 1. It's the number that when you multiply it by when you multiply anything by it, it doesn't change. So no matter what number I give you, if you multiply it by 1, you get that same number back. That's all it means to be an identity. Now, an inverse for a number is a unique number based on the number you start with. So if you start with the number 3/4, your inverse will be a different inverse than if you start with the number 6/52. Okay? So an inverse is a number that you multiply by, and you get back to the identity, the number 1. So you guys have seen this before, but if you have a number, we'll do 6/52 because it sounds like a good place to start. 6/52. The question would be, what would I have to multiply here to get the number 1? And what do?
Flip it.
You flip it. Right, so you end up with 52/6. That actually reduces. I didn't come up with a very good non-reducible example, but it still holds the same. The property still holds true regardless. So an inverse is actually just the reciprocal. That's what we call it, right? When we flip the fraction upside down, it's called a reciprocal. It's the reciprocal of the fraction I started with. And it actually works for whole numbers too. Like let's say, for instance, I had the number 3. What would I have to multiply 3 by to get back to the number 1? 1/3. Right? So it doesn't really look like it as it's written right now, but 3 is really just 3/1. You guys remember that? Okay. So we have all of these rational numbers, whether they're whole numbers like 3 or whether they truly look like fractions like the 6/52, have a multiplicative inverse. There's exactly one number that does not have a multiplicative inverse. Do you know what it is? 0. And that's why you see in this definition it says non-zero, because you can't flip 0 and have another number that's actually defined, right? 1/0, in other words, is not a defined number. It doesn't have a value. All right, couple others. Properties. The distributive property. This property we encounter in this particular textbook when we talk about whole numbers as well, and integers for that matter. The distributive property of multiplication over division simply says that if you have some rational numbers and you've got one of them on the outside of a set of parentheses and you want to multiply them by the sum that's on the inside, you could distribute the multiplication over the parentheses and then do the addition afterwards. And the same thing would hold true if that addition said subtraction. There's nothing special about that. And the multiplication property of equality simply says that if you have two numbers that are equal and you multiply them both by a fraction that's the same fraction, they stay equal. For example, if you had the number 3/1 and the number 6/2, and you multiplied them both by 4/7, you'd have the same fraction to start that you started with. I mean, they would still be equal, I should say it that way. The two fractions would still be equal that you started with. And we use this property, this multiplication property of equality, a lot when we solve equations. A lot. And in fact, I think that's what we're headed to next. So one more set of properties, and then we're going to do some equations. This is the multiplication property of inequality. The multiplication property of inequality is used when we have inequalities. And what it says is if we have two fractions, one's bigger than the other one, right? The A over B is bigger than C over D, and you multiply them both by a value that's positive, then the direction of the inequality stays the same. In other words, if I had 5 is greater than 3, and I multiplied them both by 2, I'd have 10 greater than 6. That's all that's saying. Now, the second line says something quite different, though. The difference actually comes into play where it says I'm multiplying it by negative. So again, if I took that 5 greater than 3, and I multiplied both sides by -2, so I had -10 and -6, that greater than sign would turn into a less than sign. And again, the reason is because when we introduce negatives, we flip that number line to the other side of the number line. Kind of like the problem you were talking about at the beginning, Hannah, right? Because we've got those negatives, it changes the direction of the ordering, right? Big negative number is actually a very small number, or a number that's very far left on your number line. All right, last one, number 4, says the multiplication property of 0. And all it says is that when you multiply by 0, what happens? You get 0. That's all it says. Okay. All right, let's take a look at an example on how we use these properties. Example number 2 says to solve for x, and we encountered this last time. We talked about solving for x simply means doing what? Right, getting x all by itself on one side. So our goal is to say x equals, ta-da, we're done. Okay, that's our goal. So on this one, I have a 3 over 4 that is multiplied by the x, and I need to move it to the other side somehow. So what am I going to have to do? Subtract won't work. Okay, why first will subtracting not work? So they're actually multiplied. So we have to keep in mind what the operation is. So this one's an operation of multiplication, and the opposite of multiplication is actually division, which is true, but there's maybe another nicer way of doing that because fractions are involved, and I don't really want to divide by a fraction. Multiply by the reciprocal. Okay, so we're going to multiply both sides by 4 over 3. What in the world property allows me to say that I can simply go and multiply both sides by 4 over 3? Not quite, but you're getting close. We're going to use that property in just a second. The 4 over 3 is the one we want because it's the multiplicative inverse. That's why we want it. But what is it that allows me to actually put that 4 over 3 on both sides? No, I don't have any distribution because distribution takes things multiplying over an addition sign. This is the multiplication property of equality. It's number 2, right? Number 2 says I'm allowed to multiply both sides by e over f, and it won't change the answer's value. It won't change the original two values of the, it won't change the original equality, let's say it that way. So this is the multiplication property of equality. That's what we're using there. Now, what is 4 over 3 times 3 over 4? That is 1. Now I know that we don't normally write 1x, but I want to show you that the property that you're expecting to have here actually works. So this is 4 over 15 on the right. 1, that 4 over 3 times 3 over 4 turning 1, that is your multiplicative inverse property. Right? Multiplicative inverse says that when you multiply a number times its inverse, you get 1. There's actually one more property here that's saying 1 times x. What is 1 times x? X, this is the step we usually skip. We usually go to straight here, right? But 1 times x is another property. What's that? Multiplication something. That is the multiplication identity or multiplicative identity. Multiplicative identity says if you multiply something by 1, it doesn't change. Okay? But that one didn't have very many steps, so let's do one that does. This one has fractions. It also has some multiplication times the x, the 2 over 3, and then times the x. And we've got the addition and subtraction that we encountered in the last section. Right? So this one kind of combines everything from 6.2 into what's going on in 6.3 now. There are lots of different ways to approach this problem. Okay? So somebody suggest for me where you would like to start. What would you like to do first? Okay, you want to get a common denominator on the bottom. Is that okay with everyone? I mean, eventually we're going to have to do that at some point anyway. Is that okay to do now? All right. So, Shana wants us to get a common denominator on bottom, and 12 will be a good choice, right? So they all have the ability to be changed into 12. So 2 over 3, that fraction gets multiplied by what?
4,
so 4 over 4. The 1/4 is going to get multiplied by 3 over 3. The 1/6 or the x over 6, 2 over 2. And the 1/2 by 6 over 6. Okay, so I jotted those in there, and now let's just do the multiplication like you said. All right, so the 2x is actually going to become, like you said, 8x over 12. 3 over 12. 2x over 12, right? Don't forget the x. Okay, so what did we do? I mean, what allows us to make this move? So we're playing a game, and there's a rule book. What's the rule that allows us to do this? You're close. I mean, it didn't actually change anything, which I think is what you're getting at, right? I didn't change any of the values. These are equivalent fractions. That's one way to say it anyway. We did that back in section 6.1 when we were talking about how to make a fraction equivalent to a fraction we'd had before. So equivalent fractions is a good way to describe what that did. There's actually another step right here that you might really want to use that would make things so much nicer. We will. That's what I'd like to do. Would you guys like to multiply by 12? Yeah. Do you know why that would be so nice?
Because you don't know fractions.
There's no more fractions. Yeah. Why not, right? Because that makes the problem easier. And if we can make a problem easier to work with, then we're probably less likely to make a mistake in working with it, right? Just the reality. So let's actually multiply both sides by 12. And in doing so, I get 8x plus 3 equals 2x minus 6. What is it that allows me to multiply both sides by 12? What is that? We are using the distributed property in doing it, so I'll write that one down, but there's still something else going on. Yeah, it's the multiplication property of equality. Remember, the multiplication property of equality says I'm allowed to do something as long as I do it to both sides of the equation, in multiplication terms anyway on this one. Yes?
So could you minus the 2x over 12 over, like put them on the right side and then times them by 12?
Yeah, you could.
Would it make a difference?
No, it wouldn't. And you could keep the 12 in the denominator
Yeah.
all the way through too if you wanted to. You wouldn't have to do that at all. I'm just kind of a fan of simplifying what it looks like, and so I kind of like the idea of eliminating the fractions if I can. All right, so I've heard two of you tell me you want to move a 2x though now, so I'm going to do that next. So we're going to subtract the 2x. What in the world allows me to subtract the 2x?
Is that the multiplication property of equality?
You're really close, but I'm not multiplying this time. It looks like subtraction. We don't have any properties that actually have the word subtraction in their label though, so. It's the same as being addition of -2. So we're going to call it the additive property. We saw that last time, but we didn't do very much with the properties too much last time. This is the additive property of equality because subtracting the 2x is the same as adding a -2x. Would you guys be opposed to me moving the 3 at the same time? So I could do minus the 3 to the other side. So now on the left I have what? 6x. And in reality, let me just write this in so that you can see it happen once. You don't have to write this every time, but I do want you to recognize that there's a property here that we, again, don't usually write. And then we've got this 0 right here, and then minus the 9. The fact that the 3 and the -3 and the 2x and the -2x becomes 0 is actually another property. That's the additive inverse property, right? It's the property that says when you add a number to its additive inverse, it gets back to the identity of 0. And then when you add the 0 to any number, right here, the reason that was able to happen, that the 0 is because this is the additive identity. You have no idea how many properties you use when you solve equations, because we just do it, right? We don't really think about why we're allowed to do that usually, but there are definitely reasons why we've been allowed to do those different things and make the property and have the property have the property of equality hold. We'll say it that way. What are we going to do next? Divide by 6. Do you know what property it is that you're using when you divide by 6? Because we don't have any properties that say division. That is a multiplicative property of equality. Because when we divide by 6, do you know what we're really multiplying by? The reciprocal, 1 over 6, right? So this idea of division really is just a multiplicative trick a little bit. I mean, it's just multiplication in a different way. When I do this, I end up getting really 1x equals, and we'll simplify this just because we can. I've got negative what? Negative 3 halves. So there's two things that I did. One, I simplified the 6 over 6 into the number 1. That's the multiplicative inverse. And then the simplifying the negative 9/6 into negative 3 halves is equivalent fractions. Kind of like I started with at the beginning when I created them to all have the denominator of 12. And last but not least, I can write that 1x is equal to x, and if I do that, what property am I using to say that 1 times x is x? That is the multiplicative identity. Very, very well done. Okay? There's going to be some problems that you're going to have in your book where they're going to have lines written to the side that are asking you to identify which properties used on which step. And so that's where this is sort of heading, is that you're going to be identifying what they've done in certain problems and the steps that they go through. All right, what's next? Division. Well, we tried to divide, and I told you just a minute ago that it was just really glorified multiplication, right? Or at least a little bit of a different way of interpreting multiplication. So division of rational numbers. If a over b and c over d are rational numbers and we want to divide them, and they do in fact have a value that is their answer, e over f, then that works if and only if we were to multiply the c over d times the e over f. And again, I'm going to use some whole numbers to show you that this works, because this is exactly what you know works with division. In fact, it's usually the way that you encounter division the first time. 6 divided by 2 equals 3. So one of the ways that we first introduce the concept of division is we say something like this. 6 equals 2 times what? Well, the answer is 3, right? So when we present it in terms of multiplication, which is exactly what's happening down here, they've written theirs as 2 times what equals 6. We can see that division problem turned into multiplication.
In high school, we were taught this rhyme to remember how to do that, and it was...
Hold on. You were taught a rhyme for what I'm about to do next.
Okay.
So let me just say 2 words, and then I want you to tell me your rhyme. Okay? Now, in reality, this definition is not how we go about doing division of fractions, right? It's actually just telling you what division is. But when we do a division of fractions, there's a different algorithm or a way in which we do it. So you tell me your rhyme now. It's your turn.
Okay, it said, when dividing fractions, don't be shy, flip the second and multiply.
Excellent. Did anybody else have a acronym or anything that helped you to remember how to multiply or divide with fractions?
Could you say that again? I didn't hear it.
When dividing fractions, don't be shy, flip the second and multiply.
And it's been a while since I'd heard one. There's one I heard a while back. I'll see if I can remember it and come back with it later. Obviously, the ending result is exactly what you've said, but another way of sort of a mnemonic device to remember. So you guys probably do remember that division by a fraction is simply taking that piece that you're trying to divide by and multiplying by the reciprocal, right? Hannah mentioned that earlier when we were doing that last problem with dividing by 6, the same as multiplying by the reciprocal, multiplying by the flip of the fraction. And that's a great tool to be able to divide, to change your division into multiplication. But it kind of looks a little bit like magic, right? I mean, like I just turned something that was division into multiplication, and why in the world did that work? Kind of an answer or issue. So what I want to show you is I want to actually show you why it works, that you really can do this flip and multiply business. Okay? So we're starting here with the question of what in the world is A over B divided by C over D? So our goal is to figure out what in the world is this division. You guys with me so far? Okay. What I'm going to do is I'm going to write the A over B in another form as a numerator of the fraction with the C over D in the denominator. All right, that little division sign between them, we often will write something that looks like a little division sign as a bar for fraction bar. So far, so good? Okay, the next thing I'm going to do is I want to make this C over D, the denominator of this fraction, go away. Well, what do I have to multiply C over D by to make it turn into the number 1? D over C. That's the multiplicative identity. But when I'm working with fractions, that is the big, overarching, ugly fraction I've got right now, if I multiply by D over C, on the bottom, I have to multiply by D over C on the top. In essence, what I end up with is the A over B on top times the D over C. What's on the overall bottom of this fraction now? 1. So I end up with A over B times D over C. And it's using this idea of it being a multiplicative inverse in order for me to be able to do this flip and multiply business. Okay? So that's where that's coming from.
When we do our homework,
Mhm.
do we need to show that multiplication of it, or can we just automatically?
Oh, this
do it?
particular piece here?
Yeah.
No.
Okay.
I just want you to recognize why it's happening.
Okay.
And I don't even expect you to remember this a year from now. I'm not saying that you will. You won't. But if you've seen it once and you have that kid in your class that wants to know why, you should be able to research why, whether it's going back to notes from this class or whether it's looking on the internet and looking at it and going, oh yeah, I remember that's what we did and we've seen that before, that kind of thing.
Okay.
So that's why I'm bringing it up, is
Okay.
because you guys are going to have those kids that are going to ask questions of why. I've got one in my house. Okay? You may too one day. All right, I want to do one more slide and then we'll stop and do some group work. This slide talks a little bit about division. It is very common, I'm going to just have you look for a moment with me at example 5. It is very common for students to not understand what 6 divided by 1/2 means, because we don't really talk about division by fractions much. And the reason we don't is because our ideas of division usually have to do with taking something and like dividing it among people or something like that, right? So for example, on the first one way to talk about 6 divided by 2 is to say, I have 6 cookies and I've got 2 kids. How many cookies does each kid have? Well, that doesn't work very well on the next example. I have 6 cookies and I have 1/2 kids. Somehow it just doesn't really work. So what are we going to do? Well, there's actually another way to think about the 6 and the 2 and the numbers of kids and cookies, okay? So what I'm going to do is I'm going to say we have 6 of whatever you'd like. So we have 6 cookies, rocks, cupcakes, I don't care what you want to do. We probably do rocks. I don't think we're going to be able to divide the rocks. So we have 6 cookies, and instead of dividing them into 2 groups, which is sort of what I suggested at the beginning, we're going to separate them into groups of 2. Now, you may hear that and think, I don't get it. That sounds like what I just said not to do. But there's a difference. Okay, so here's my 6 cookies. Previously, I told you we have 6 cookies, 2 kids, and if I separate them, that means I've got 3 cookies per kid, right? 6, 6, okay. What that did is that created actually 2 groups, didn't it? Okay. Well, instead of doing it with creating two groups, I want to create groups of size 2. Okay, it's a different way of dividing. Now my groups have size 2, and how many groups do I have? 3. So imagine taking, like you're at a bake sale and you've got these cookies, and instead of deciding you're going to create 2 baggies of cookies, you want to create bags of size 2 cookies. In other words, you want to put 2 cookies per bag. So if you did that, then you would be able to sell 3 different bags of cookies. Each bag of cookies has 3 different bags of cookies. Each bag of cookies has 2 cookies in a bag. All right? So we can use this idea actually with the lower example. So I have my same 6 cookies. You might want to imagine, however, big cookies like McAllister's cookies for this to really work so well for you. They're so good, I know. If you've ever been to City Bites, City Bites has very good cookies like that too.
You know where else? DC Cakes.
Very good to know. Now we're all hungry. I have 6 cookies. Previous example, I wanted to make groups of size 2. So how could I word this to work with the number 1/2?
Are you basically like taking 6 cookies and dividing them all into 2 pieces?
We are, because we're creating groups of size 1/2 cookie. So imagine if you were doing this bake sale, and instead of putting 2 cookies in a bag, you put in half of a cookie in a bag. And if they're big cookies, then that might be acceptable, right? I don't know. Probably not. But so here on this one, let me write down that language. This again is your 6 cookies, and you separate into groups of, and I'm going to put the word size in here just because it helps give us some of that context that we like, groups of size 1/2. And so just like you guys said, that means I'm going to split all my cookies into groups, or into 2 pieces of a cookie. And now if you count, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 halves of cookies. So the division by 1/2 does not mean I'm actually dividing each of the cookies in half. In essence, that's what it works out to being visually. But it's because I'm making the cookies a size 1/2. Okay? Any question on that one? Okay, this is actually a really good place to stop, because the other part of the lesson is quite different in nature.